Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to part 3 of chapter 9 self-induction. At the end of this video, the student will be able to read the graphs of the growth and the decay of a current in RL series circuit, establish the differential equations of the growth and the decay of the current in RL series circuit and give their solutions, know the physical significance of the time constant. The remaining objectives will be discussed in the next videos. Now, as a summary from the previous video, a coil of inductance L and traversed by a current I is the seat of self-induced EMF E equal minus L di over dt. The potential difference across the terminals of the coil of inductance L and resistance R is U coil equal to Ri plus L di over dt, and if E times I less than 0, in this case the coil acts as a receiver, while if EI greater than 0, in this case the coil acts as a generator, and if I is constant with time, then di over dt equal to 0 and E equal to 0, so in this case the coil acts as a pure resistor. In order to obtain the differential equation in the case of growth of the current, let us set up the circuit as shown in the adjacent figure. In this circuit, we have a square signal generator giving a constant voltage E in the first half period and a voltage of 0 volt in the second half period. And on the screen of the oscilloscope, we are visualizing on channel 1 UAC, which represent the voltage across the terminals of the generator, and on channel 2 the voltage UBC, which is the voltage across the terminals of the resistor. Now, in order to obtain the differential equation, we will use the law of addition of voltages. As we know, UAC equal to UAB, which is the voltage across the coil, plus UBC, which is the voltage across resistor. Now note, during the growth of the current, the voltage across the generator UAC is equal to E. So E equal R prime I plus L di over dt, which is the voltage across the coil, plus Ri, which is the voltage across the resistor according to Ohm's law. So E will be equal to R prime plus R into I plus L di over dt. Now let R capital be equal to R prime plus R, so we will obtain di over dt plus R over Li equal to E over L, of course after we divide by L. Now this is the differential equation of the first order that governs the variation of the current I during its growth under a constant voltage. So the differential equation will have the form di over dt plus R over Li equal to E over L. Now, in order to obtain the differential equation in terms of UR, we use also the law of addition of voltage UAC equal UAB plus UBC. So E equal R prime I plus L di over dt plus UR. Now, since UR equal Ri, so DUR over dt will be equal to R di over dt. So di over dt will be equal to 1 over R times DUR over dt. So we will have E equal R prime over R times UR plus L over R DUR over dt plus UR. Now we will take UR common and we multiply by R and divide by L. We will have DUR over dt plus R prime over L multiplied by UR equal to RE over L, which is the differential equation that governs the variation of UR in terms of T. The solution of this differential equation have the form I equal I maximum into 1 minus exponential minus T over tau, where I maximum equal to E over R total and tau equal to L over R. Tau is called time constant, and it represents the time needed by the current to reach 63% of its maximum value. Now, in order to verify the shape of the curve, let's take some particular values. For t equals 0, we will have I equal I maximum into 1 minus exponential to the power minus 0 over tau. As we know, e to the power 0 is 1, so I maximum into 1 minus 1 will be equal to 0. So at t equals 0, the current was equal to 0. Now, for t equal tau, we will have I equal I maximum, 1 minus exponential minus tau over tau, so it will be equal e to the power minus 1 will be equal to 0.37. So I equal I maximum 1 minus 0.37 equal to 0.63 I maximum. So for t equal tau, the value of the current reaches 63% of its maximum value I. Now for t equal 5 tau, we will have I equal I maximum into 1 minus 0.007, which will be equal to 0.99 I maximum. So at t equal 5 tau, the value of the current is approximately equal to its maximum value I maximum. Now, the shape of the curve can be divided into two sections or two phases. The first phase is called the transient phase, which the current I is growing from 0 to I maximum, and the second phase is called the steady phase or steady state, where the current is constant. Now let's solve application 4. Consider the circle in the adjacent document. The differential equation that governs the variation of the current I during the growth phase is E equal Ri plus L di over dt. Show that I equal I maximum into 1 minus exponential minus t over tau is a solution for the differential equation where I maximum equal E over R and tau equal L over R. Now first, I equal I maximum into 1 minus exponential minus t over tau. Let's expand the expression of I. We will have I equal I maximum minus I maximum E minus t over tau. Now, we derive I with respect to time, so we will obtain di over dt equal I maximum over tau E minus t over tau. Substitute in the differential equation, we will have E equal R into I maximum minus R into I maximum E minus t over tau plus L I maximum over tau E minus t over tau. So, since I maximum equal E over R and tau equal L over R, we will get E equal E minus E exponential minus t over tau plus E into exponential minus t over tau. So we will have E equal to E, which is true. So I equal I maximum into 1 minus exponential minus t over tau is a solution for this differential equation. Now, in order to find the time constant tau, we have two methods. The first method, simply for t equal tau, I will be equal to 0.63 I maximum. So graphically, we search for I equal 63% of I maximum, and the abscissa of this point is tau. Second method is by calculating the slope of the tangent to the curve at t equal 0. As we know, the tangent to the curve I of t at t equals 0 has a slope equal to di over dt at t equals 0. In order to determine the value of this slope, we derive the expression of I with respect to time. We will have di over dt equal I maximum over tau into E minus t over tau. Now this expression represents the slope at any time. In order to obtain the slope at t equals 0, we will replace t equals 0, and so we will have di over dt equal I maximum over tau, and this is correspond to the expression of the slope of this line at t equals 0. Now this line, according to the graph, in order to calculate its slope, we can say that the tangent of this angle is equal to the slope of this line, and it will be equal to the opposite over the hypotenuse. The opposite is I maximum and the hypotenuse is T1. Now by comparing di over dt at t equals 0 and tangent theta, we will have I maximum over T1 equal to I maximum over tau, so T1 represents the value of tau. Now, in order to determine the differential equation in the case of decay of the current, we will use also the law of addition of voltages, UAC equal to UAB plus UBC, but now in this case, UAC equal to 0 in the decay of the current. So, R prime I plus LdI over dt, which is the voltage across the coil, plus Ri, which is the voltage across the resistor, equal to 0. So R prime plus Ri plus Ldi over dt equal to 0. And if we take R capital equal R prime plus R, so we will have di over dt plus R over Li equal to 0, of course, after we divide by L. And this is a differential equation of first order that governs the variation of the current during its decay under a constant voltage. Now the solution of this differential equation have the form I equal I maximum E into minus T over tau, where tau now in this case is the time constant needed for the current to decay to 37% of its maximum value I maximum, and tau in this case also equal to L over R. Now, if we take some particular values, we will have for t equals 0, I equal I maximum, E minus 0 over tau, so it will be equal to I maximum, which is the starting point. For t equal tau, I equal I maximum E minus tau over tau, so it will be equal to I maximum E to the power minus 1, which will be equal to 0.37 I maximum. So for t equal tau, the current I drops to 37% of its maximum value I maximum. And finally for t equal 5 tau, I equal I maximum e to the power minus 5 will be equal to 0.007 I maximum. So for t equal 5 tau, I approximately reaches 0. Now let's solve application 5. Consider the circuit in the adjacent document. The differential equation that governs the variation of the current during the decay phase is Ri plus Ldi over dt equals 0. The question here, I equal A e to the power bt, is the solution of the differential equation. Determine the expressions of the two constants A and B as a function of L, R, and R prime. So since I equal AE into bt, we determine the derivative of I with respect to time. So di over dt equal to A times B into E to the power bt. Substitute I and di over dt in the differential equation. We will have 0 equal R into AE to the power bt plus R prime AE to the power bt plus LA times B into E to the power bt. We will have 0 equal R plus R prime plus LB into A times B to the power bt. Now, as we know, the expression of the exponential is different from 0. So A dot E to the power bt is different from 0. And we will have R plus R prime plus LB equal to 0. So B equal minus R plus R prime over L. Now, in order to determine the expression of A, we will use the initial condition. In this case, at t equals 0, I0 equal to A e to the power 0, which is equal to A. So A equal I0, which was the value of the current at the beginning of the decay, which will be equal to I maximum. So A equal I maximum. Now, as a summary, the differential equation during the growth of the current is di over dt plus R over Li equal E over L. The solution of the differential equation di over dt plus r over li equal e over l is I equal I maximum into 1 minus exponential to the power minus t over tau, and the differential equation during the decay of the current is di over dt plus r over li equal to 0, and the solution of this equation is I equal I maximum into e minus t over tau. And tau is called the time constant. It represents the time needed by the current to reach 63% of its maximum value during its growth and 37% of its maximum value during its decay, and the unit of tau in SI is second, and tau equal L over R total. This is the end of part 3. Thank you for your listening.